earlier, the algebraic concepts unit really introduces you to a whole bunch of tools that you then use in this unit, which is the polynomial functions unit, and then we do trigonometry, then trigonometric unit, exponential functions, logarithmic functions, a whole bunch of different kinds of functions that we tackled during the year. So this is a polynomial functions unit, and I want you to think of functions as kind of like if I had to apply them to real world, what I'd be saying is that what typically happens is that you've got a circumstance, an issue. It might be some data that you've collected as a scientist or as a social scientist, like a survey data, or it could be climate change data. It could be lots of different kinds of data. And then what you do is you basically look at the data and you plot the data, graph the data, and then you say this data seems to be tending towards a certain shape. And it might be an exponential shape, or it might be a logarithmic shape. Don't worry about what that means. It might be cyclical, which is like a trigonometric shape, or it might be a parabola shape, or it might be a straight line. All of these things can be, if there's any correlation at all to the data, form a line of some description that can fit to a certain rule. And so what we do is we develop techniques to create that rule. And by creating that rule, we're then able to use that rule to explore further. So we can do sort of what-if scenarios, or what if I change this part of the rule, or what if I change this part of the rule? Does it mean that we're all going to die in 2030 instead of 2035 by climate change, something like that? It allows us a little bit to sort of extrapolate into the future and say, well, what's going to happen in 50 years' time if this rule fits for the next 50 years? Or it allows us to see what's happening inside the data that we've got, maybe for a data point we don't have, but the rule can approximate what would be happening in that time, all that kind of stuff. But it starts with the capacity to manipulate or to come up with the function, the rule, which is what we call a function, and then be able to understand what that function does. And so in this first unit, we look at polynomial functions, a particular family of functions called polynomials, and I will unpack those in a second. But generally speaking, functions in general, you don't really have to write this little bit down, but generally speaking, when we study functions, we're studying the shape, we're studying critical features. And for different functions, we have different critical features. Each function has a basic shape, which can be stretched out or moved. Each function has critical features. Now, what those critical features are depends on the kind of function it is. So I'll give you an example. I'll just verbalize it, though. For example, things that you are already aware of. X-intercepts. You've heard of those before, I hope. Really good for working out when what's happening at the base level of something. Y-intercepts, I'm sure you've heard of. That's really good for understanding what's happening at the start in a real-world scenario. Gradient, yeah? The slope of the line. The bigger the gradient, the faster things are happening within the function. The flatter the gradient is, the slower things. The direction of the gradient is positive or negative. Those kinds of things. What else? In a parabola, what's another critical feature of a parabola? Do you know? Yeah, turning point. So turning point's another one. In other graphs, for those who have done Maths Extended, this will make sense to you. If you haven't done Maths Extended, you're going to go, what the now? And that's okay. Asymptotes, which are lines that the function approaches but never hits. That's about it, really. That's the main critical features. So in our exploration of graphs, functions, that's what we're doing. We're going to say, what does the shape look like? What are the critical features? Can I identify them so that I can form a graph, form a rule from a picture of a graph? Or if I'm given a picture of the graph, or if I've been given the function, can I form the graph? That kind of thing. What we're focusing on, I'll move on to this first. This is probably worth writing down. You know what, I'll keep it zoomed out now so you can see the whole context. So what is a function? So you should know this already, but it's okay if you don't. And I think it is so critical to understanding what happens next for the rest of the units. I'm going to spend a moment talking about it. So you can see what I've got there. A function is a rule, and I'll try to be as simple as I can. It takes on an x value. We call that the input value to the function. And then it produces a y value. So the rule is what, how do I put this? The rule is what causes the transformation to the y coordinate. Okay? So I'm going to put some examples down. And if I could just have a show of hands in the air, who's seen that notation before? Just a few of you. So I'll talk about it in a second. Is anyone who put their hand up there is brave enough to say how you would say that? There's no trick. It's if you've heard it, you'd know. F of x. Yeah, that's how you say it. F of x. That means it's a function whose input is x. That's what it means. It's a function f whose input is x, and it outputs y, right? Which is often why you see the rules written as y equals 3x plus 1. The rule is 3x plus 1. Y is the output. The function is f of x equals 3x. But I'll just put a few examples. We will come across all of these examples over the course of the year, but not all these are polynomial functions. F of x equals 3 to the power of x. F of x equals 2x plus 1. F of x equals x cubed minus 5. F of x equals 1 on x. All of these are examples of functions. The right-hand side here, this tells us the rule. This tells us when I input into my function a number, what comes out. When I input 1 into this function, what comes out? 3. When I input 2, what comes out? 9, not 6. When I input 3, what comes out? 27. See what I mean? So in terms of the function, we then have what are called ordered pairs of ordered pairs. It's a bracket, and then the input value, the x, comma, and then the output value, which is the y. We call them coordinates, right? But a coordinate is an ordered pair. The first number is the input, the second number is the output. The first number is x, the second number is y. When I put those points onto a piece of paper with axes on them, we can draw a graph. Okay, I've got a little bit more about graph drawing in a second, so I won't say anything more about that. And that second text box there, it's up to you what you write down there, but I just wanted to put it out there that there are heaps of different kinds of functions. In this unit, we are exploring polynomial functions. It's probably worth putting that bottom phrase down there, though. A polynomial function is made up of terms where the powers of x are positive integers. Positive integers. Technically, you could also include 0 there, but it's a bit of a boring one if you include 0. So, of the list here, is this a polynomial function? No, because the x is a power. It's not a term to a power. The x is the power. So that is not a polynomial function. Is this a polynomial function? Look at the terms. Are they terms that are made up of powers of x, where the powers of x are positive integers? Yeah. That's 2x to the power of 1. Yep. So that's fine. And that's just a constant. We call that the constant term, the term with no values of x. That's fine as well. Okay, so that is a polynomial function. P.S. If I said 2x plus 3 to the power of x, that would not be a polynomial function either, because the 3 to the power of x rules it out. This one here, is that a polynomial function? Starts with y, ends in s. Yes, good. It's a polynomial function because the x power is 3. That's fine. The minus 5 can sit there as well. That's fine. 1 on x, is that a polynomial function? No, it's not. And I'll explain why. I can change that to x to the minus 1. So if there's an x as a denominator, it's not a polynomial function. Okay? So that is not a polynomial function. Did you say square root function, someone here? That's not a polynomial function either. Yep. So the square root function, I'm glad you raised it though. I'm just going to put it up here under test handback. You don't have to write it down. The square root function looks like this. That is also not a polynomial function because it can be written as x to the power of a half, which is positive, tick, but it ain't an integer. So I don't know if I describe what an integer is. An integer is a whole number. Okay, so it has to be a whole number that's positive, or technically zero is fine as well. Everyone okay with that? Solid? Yo, yo, yo. Okay, so don't write this down, this bit in slide 2 there. I just want to say that polynomial functions in this course are limited to powers of 1, powers of 2, or powers of 3. So linear, quadratic, and cubic. That's as high as we go. We don't go any higher, so there will be no x to the power of 4 graphs, etc. Of course they exist. You'll do them in level 4 if you choose to go on next year, but you don't do them in level 3. And I think I come back to this in the video actually later, so I won't dwell on it. But another way of saying that is that the polynomial functions will have a maximum order 3. So when you say the order of a function or the order of a polynomial function, it means look at the function. What's the highest power of x? That's the order of the function. So if I had f of x equals x squared plus x to the 7 minus x cubed, that would be an order 7 function, an order 7 polynomial. Yeah? That's all it means. It's just language. Okay, so we're going to start by looking at linear functions, which is something you really have done at least since year 8. So I hope I can go fairly quickly through it. But what I'm going to do is I'm going to take the approach to linear functions that you need to take across, excuse me, take across all function types that we look at this year. And that is, we consider the function, we consider what it looks like, shape of it. I didn't put that down here for linear because it's pretty straightforward. We then look at what the critical features are of that graph, or that function. So for linear functions, you should know what a linear function is, a straight line graph. The critical features are as follows. It has an x-intercept. Does it? Usually. Anyone give me an example of a linear function which doesn't have an x-intercept? Sorry? Let's assume it goes on forever in both directions. If you're talking about an asymptote kind of idea, linear functions don't have asymptotes. Tom? On the y-axis? That'll work. Or anything parallel to the y-axis. But can anyone give me an example of a function that would do that? Y equals 5, that'll do. Or y equals minus 5. So anything parallel to the x-axis would work as wouldn't have an x-intercept. On the x-axis, that's got an x-intercept everywhere, I suppose, doesn't it? Y-intercept, always. A gradient, always. Like a horizontal line that has a gradient of? Zippity? No gradient. It has a gradient, but the value is 0, right? The gradient is 0. A flat line that is a gradient of 0. This, if you draw a straight line like this, that you can graph that, but it's not a linear function. We'll talk about that later, I think. Okay, you can see there on slide 4, I've just got a really rough idea of gradient. I want to introduce you to sort of a concept of how to describe gradient. Gradient. Oh, Charlie, any questions? Go for it. You sure? Oh, sorry. Would you just tell me to translate if I need to? You got it? Worked it out? Sorry about that. So we're on slide 4 now. The gradient. I think you should be familiar with the idea that we can express the gradient numerically by looking at the ratio or the fraction formed from rise compared to run. Yeah? That's the rise and that's the run. So typically, If the rise is really big compared to the run, then you're going to have a big number. And if the rise is really big, you're going to have a really steep line. So the bigger the number of the gradient, the steeper the line is. Similarly, if I have a really tiny rise and a really long run, then it's going to be fairly flat. Okay, so you'd expect a fraction, a small number, to be flatter than a big number. Then we've got positive and negative gradients. So this is a positive gradient because as the rise increases, so does the gradient, so does the run. If it was a negative gradient, like so, then it would be going, the rise would be going down. So it's not a rise, it's a negative rise. So the rise would be going down with a positive run, or we'd be going backwards. So we'd be going for a negative run and then a positive rise. Whichever way you look at it, you're going to have a negative divided by a positive, which gives you a negative number. So again, gradient, size equals steepness, sine equals which way it's going. Left to right up or left to right down. Good with that? Not blowing anyone's minds yet, I hope, because this is familiar stuff. This is something that I might just zoom up just so you can sort of see where I'm at. This is where you might not be quite familiar with this terminology, so I'll explain as I go along. The gradient could be expressed as delta y over delta x. Now, when I write delta in this context, it means a change in. Really common in mathematics to use delta to describe the change. So what I'm saying here is change in y over change in x. So if I can quantify how much the rise is, how much the change of y is, and then I quantify how much the rise is, the run is, then I can come up with my number. So this typically gives rise, lol, to the gradient formula, which you should be familiar with. y2 minus y1, that'll give you the change in y, over x2 minus x1, and that'll give you the change in x. Yes, yes, yes. This is hopefully not, this is just a refresher for everyone, I hope. Okay, so again, we take our coordinates here, and by default, just it doesn't matter which way you do it, to be honest, but I'm calling this one x2, y2, and the one down below, I'm calling that x1, y1. So I'm saying that that difference there, that change in y, would be found by taking y2, which would be the distance all the way up, and taking away y1, which is the distance just up to here. So y2 minus y1 will give me the change in y. x2 minus x1 will give me the change in x. So that's where that formula comes from. And it's a matter of plugging it in. So I've got an example here that I'll do for you. Really simple. So if I was told that a line passes through 3, 5, and 5, 10 and find the gradient, all you're doing is you're saying, well, it doesn't matter which way you go. You can identify the first set or the second set as x2, y2, as long as you just keep the x2, y2 together and the x1, y1 together. Never do x1, y2. That won't work for us. Okay, so quite honestly, I just go, okay, I've got a 10 and a 5 here. So because 10 is bigger than 5, I'll just go 10 minus 5 all over, and then I'll go 5 minus 3. I do my equal signs underneath each other normally, but I'm squishing it in. 10 minus 5 is 5. 5 minus 3 is 2. That can't be simplified any further. You could change it to 2.5 if you want. Could change it to 2.5 if you're fraction phobic, but 5 over 2 is the gradient, it's fine. And in fact, for gradient, keeping it as a fraction is kind of better. It kind of basically means for a rise of 5 units, I'm going to go across 2. And it gives you a sense of the steepness of it just by thinking about it in that way. Anyone got any questions on that? That's not too bad, is it? What's the time? 12:50. Okay, real quick. Example 2 here. And then I'm going to have to get you to do this for homework, please. If you can't do this for homework tonight, because if you can't, as opposed to won't, if you can't do it for homework tonight, no dramas, just let me know on your way out that you just can't possibly do it. But if not, the more you do of this, the better you're going to be. It is just gradient work, so it shouldn't be too dramatic. So example 2, a line passes through 2, 5 and 4a. Find the value of a. Okay, so the way I do this is I would set up as m is equal to Oh, hang on, gradient of -2. I actually wouldn't even do that. I would just go straight into, I know the gradient, so I'm going to put my -2 in straight away. And then I've got 5 minus A over 2 minus 4. Yeah. I think if I'd looked at it first, I might have gone A minus 5 on top and 4 minus 2 on the bottom if I'm dealing with positives, because it doesn't matter which way around you do it. As long as you consistently swap them, it's fine. If you don't believe me, do it the other way around in your book and you'll get the same answer as me. So that gives me 5 minus A over -2 equals -2. Now I'm going to multiply both sides by -2, sorry. So I'm going to get 4 on the left-hand side and 5 minus A on the right-hand side. Now I'm going to add A to both sides. I would actually do this in one step. I'll just do it for the notes in 2 steps. 4 plus A equals 5. And then, it doesn't feel right. And then subtract 4 from both sides to get A is equal to 1. No, that's right. That's basically it, right? So you either can work out the gradient, no dramas, put the 2 points you're given and work it out. Or if you're given the gradient and a point, and a missing coordinate, then you can certainly just put in the values and go for it. So this is basically like substitution and solving, something that we've done in the algebra unit. This is where you need to put it into practice. I'm going to stop the video now, but the point is you've got just under 10 minutes now. I want you to make a start on exercise 2B and then finish it for homework. So the more you do now, the better it is.